Something physical arrived from another star, not a signal, not a radio wave, not a theory. A chunk of ancient ice and gas that crossed billions of miles of deep space, entered our solar system, swung around our sun, and then kept going. Scientists called it 3I Atlas, and before it disappeared forever into the void, it did something no interstellar visitor had ever done before. It talked. Not in language, in science. In eruptions, X-rays, chemical fingerprints, and spin rates that told us exactly where it came from, how old it was, and what the universe looked like billions of years before Earth ever formed. This is the final chapter of 3I Atlas, and what it revealed about our place in the galaxy will stay with us long after it's gone. When 3I Atlas first arrived, it was cold and quiet, a body of ice and rock moving through our inner solar system on a trajectory no comet born in our neighborhood could have followed. Too steep, too fast, obviously alien. But as it swung around the sun and began its outward journey, moving away from the heat, something changed. Because comets are deceptive. Their outer crusts insulate the ice inside. Heat doesn't penetrate immediately. It builds. Slowly at first, then all at once. And that's exactly what happened. As 3I Atlas moved away, the heat it had absorbed near the sun finally reached its icy core, and the comet exploded outward in a massive outburst of water vapor, methane, and methanol. Gas jets erupted from its surface with tremendous force. Water emission rates increased by roughly 40 times. In the span of days, this ancient traveler transformed from a quiet object into one of the most active comets ever observed. Scientists had documented outbursts from comets born in our own solar system, but never from an interstellar one. And the chemistry of those gases wasn't quite right. The specific compounds pouring off its surface carried ratios and signatures that didn't match anything produced locally. This was alien chemistry, not metaphorically, literally. Then came a detection nobody was fully prepared for: X-rays. Instruments aboard multiple spacecraft began registering high-energy X-ray emissions streaming directly from 3I Atlas. As it interacted with the solar wind, the constant stream of charged particles flowing outward from our sun. This was a first in recorded history. X-rays from an interstellar comet had never been detected before. But the significance goes deeper than the discovery itself. It proved conclusively that interstellar comets obey the same physical laws as comets born in our own solar system. The charge exchange process, solar wind ions colliding with neutral gas in the comet's surrounding coma, produces X-rays the same way, whether the comet was born here or 10 billion years ago around a star we've never even named. The physics is universal. That's not a minor footnote. That's a fundamental statement about how the cosmos is built. The rules don't change depending on which star system you came from. 3I Atlas, a traveler from an entirely alien origin, played by the exact same rules as everything else in our solar system. The universe speaks one language, and we just heard it spoken by a messenger from somewhere else. Here's something that surprised even the most experienced comet scientists on the planet. 3I Atlas was spinning itself faster. At first observation, the comet had a rotational period of approximately 16.2 hours, a full rotation every 16 hours, normal enough for an object of its class. But as its outburst intensified and gas jets erupted from its surface, those jets acted like natural rocket thrusters, pushing against the comet's rotation, accelerating it with every single eruption. By the time comprehensive measurements were compiled, the rotational period had dropped to just 7.1 hours. The comet had nearly doubled its spin rate in a matter of weeks. For scientists, this raised an immediate concern. Spin a comet fast enough, and its own centrifugal force begins to overcome the internal gravity holding it together. Chunks break off, the nucleus fractures. Some comets have literally spun themselves apart, breaking into pieces that scatter along their orbital path. Whether 3I Atlas approached that threshold, and whether it survived its outward journey as a single, intact body, remains one of the open questions that astronomers are still working to answer. A comet that crossed the galaxy in one piece may or may not have survived its own eruption. For months after its detection, one of the most basic questions about 3I Atlas had no answer. How big is it? Cometary nuclei are notoriously difficult to measure. They are small, dark, and surrounded by an enormous cloud of gas and dust, the coma, that obscures the nucleus like fog surrounding a lighthouse. From Earth, you're trying to spot a small rock hidden inside that fog from 10 million miles away. But the universe offered a brief and precise window of opportunity. A rare geometric alignment between Earth, the Sun, and 3I Atlas allowed astronomers to use stellar occultation, measuring exactly how much the nucleus blocked the light of background stars as it passed in front of them. The math then converts that blockage into a physical dimension. The result: a nucleus radius of approximately 1.3 kilometers. Small by planetary standards, but for a comet nucleus that is substantial. Large enough to fully account for the massive outburst observed during its departure. Large enough to have survived billions of years of interstellar travel without being completely eroded. That single measurement unlocked a cascade of new calculations about mass, about gas production rates, about the total volume of material shed during its time in our solar system. From one number, everything else became possible. 3I Atlas was not studied by one telescope. It was studied by nearly everything humanity currently has operating in space. Europa Clipper, on its way to Jupiter, turned its instruments toward the comet and captured spectral data. JUICE, the European Space Agency's Jupiter Icy Moons Explorer, did the same. The Parker Solar Probe contributed measurements from the inner solar system. TESS mapped its brightness curve across weeks of observation. SOHO tracked it against the solar background. Mars Express observed it from orbit around the red planet. And on the surface of Mars itself, the Perseverance rover tilted its cameras upward and photographed it crossing the Martian sky. Every instrument added a different layer to the portrait. Infrared readings revealed surface temperature. Spectroscopy decoded chemical composition. Optical data tracked the dust trail left behind. Radio observations mapped the full extent of the surrounding gas cloud. The result was the most comprehensive, multi-wavelength, multi-angle study of a single comet in history, interstellar or otherwise. Scientists who had spent entire careers studying comets born in our own solar system found themselves holding a dataset unlike anything they had ever worked with. 3I Atlas didn't just pass through our solar system. It left us the most detailed portrait we have ever assembled of a visitor from another star. All of that data converged on one conclusion that is difficult to fully absorb. 3I Atlas is ancient, profoundly, almost incomprehensibly ancient. Research places its age at somewhere between 10 and 12 billion years, more than twice the age of our solar system, and nearly 3/4 the age of the universe itself. There are stars alive today that are younger than this comet. Its likely origin: the Milky Way's thick disk, a region of our galaxy populated by some of its oldest stars. Stars that formed when the universe was barely a few billion years old. Stars that have since burned through their fuel, expanded, collapsed, and in many cases no longer exist. 3I Atlas may have been launched from a system orbiting one of those ancient stars, ejected into interstellar space by a gravitational encounter, and set drifting on a journey so long that entire stellar lifetimes passed while it was in transit. But there's more. Its deuterium to hydrogen ratio, a chemical fingerprint as unique as a DNA sequence, is unusually high compared to comets in our own solar system. That ratio is a direct record of formation temperature. And what it tells scientists is this: 3I Atlas did not form near the warmth of its parent star. It formed far out, deep in the frozen outer reaches of an alien solar system, in a region so cold that temperatures approach absolute zero and chemical reactions happen over millions of years. That's where it was born. And it carried that chemistry, sealed in ice, unchanged, uncontaminated, across billions of years and trillions of miles to deliver it here. In March 2026, as 3I Atlas moved outward through the solar system, it passed near Jupiter, even from a significant distance. Jupiter's gravitational field, the strongest of any planet in our solar system, reached out and touched the comet's trajectory. The deflection was subtle, not enough to trap it, not enough to dramatically redirect it, but enough to measure with precision, and enough to factor into the trajectory models being built by researchers tracking its departure. Jupiter has played this role many times before, bending the paths of comets born in our own solar system, sometimes flinging them toward the sun, sometimes redirecting them into stable orbits, sometimes launching them back into deep space. It has now done the same to a comet from another star. The solar system doesn't just observe its visitors, it interacts with them. It changes them, even slightly, in the moment of passage. 3I Atlas entered our solar system with one trajectory. It left with another, a mark left by Jupiter, a permanent alteration. However small, written into its path forever, carried with it into the dark between the stars. Here's the part of this story that changes the entire frame. Scientists now believe interstellar visitors like 3I Atlas are not rare anomalies. They are common. We simply lack the technology to detect them before. With every generation of more capable survey telescopes, with faster alert systems, more sensitive detectors, and increasingly coordinated global observation networks, the rate of discovery is accelerating. Researchers project that next-generation survey facilities already under development could allow humanity to identify a new interstellar object every 1 to 2 years, not once per generation, not once in a career, annually. Each one would carry the chemical fingerprint of a different star. Each one would represent material formed under conditions we cannot reproduce, around a stellar system we will likely never visit. Each one would be a direct sample, a fragment of the universe as it existed in a different place and a completely different era. 3i Atlas wasn't the exception. It was the proof of concept. The galaxy has been sending us objects like this for billions of years. We just didn't have eyes open wide enough to catch them. Now we do. Here is what 3i Atlas actually was. It was a time capsule, formed 10 to 12 billion years ago, around an ancient star in a galaxy that was still young, forged from the raw material of an early universe that barely resembles the cosmos we see today. Launched into the void, by a planetary encounter, by a dying star, by forces we may never fully reconstruct, and set on a journey measured not in years or centuries but in billions of years. It traveled through darkness, through silence, through the vast empty space between stars where nothing lives and nothing waits. And then, by a cosmic coincidence staggering to contemplate, it passed through our solar system. During the brief window of human civilization, during the even briefer window of modern astronomy, during the narrow few decades when we happened to have the telescopes, the spacecraft, and the scientific understanding to actually decode what we were looking at, it erupted, it spun, it emitted X-rays, it gave up its size, its chemistry, its age, and its birthplace in a cold and distant corner of an alien solar system. And then it kept going. 3i Atlas is already beyond the orbit of Jupiter, already pulling away from everything we know. In the years ahead, it will cross the heliopause, the outermost boundary of our solar system, and return to the interstellar medium that shaped it billions of years ago. We will never see it again, but it left behind a record, a fingerprint, a set of measurements that, for the first time in the history of science, gave humanity a direct look at material born in another solar system, around another star, in another era of the universe. The galaxy is not empty. It is full of ancient travelers, and we are only just learning how to listen. If this video gave you a new way of looking at the sky above you, hit that subscribe button. Every day, we go deeper into the science and mysteries that are reshaping how we understand the universe. You don't want to miss what's coming next. Drop a comment below. Do you think we'll ever launch a spacecraft to intercept an interstellar object before it leaves our solar system, or send a probe chasing after one? I want to know what you think. Thanks for watching.